Hello everyone, my name is Saoirse Dervin. I'm a researcher from the Bendable Electronics and Sensing Technologies group at the University of Glasgow. In this presentation, I would like to share an ongoing work from our group that relates to a porous elastomer-based soft pressure sensor that can serve as a flexible and conformable pressure measurement system for various electronic and robotic technologies, including underwater sensing and surveillance. It is a pleasure to have the opportunity to share this work with you, and I would like to welcome anyone who may be listening. To begin this presentation, I would like to first provide you with a brief overview of the role of pressure sensors and autonomous underwater vehicles in water quality monitoring. I will then describe the preparation process and performance of the porous elastomer-based soft pressure sensor under pressures ranging from 0 to 300 kPa, similar to those experienced at up to approximately 30 meters below sea level, before summarizing the key points of this work and our future plans. Earth is often referred to as the blue planet because water, in the form of oceans, seas, glaciers, freshwater bodies, rivers, wells, and lakes, occupies about 71% of its surface. This water is critical for sustaining human life. Most obviously, water is needed for drinking and personal hygiene, but we also rely on aquatic ecosystems for food production, energy generation, waste management, and recreation. When waters run dry, people can't get enough to drink, wash, or feed crops. As a result, it is extremely important that we always have access to clean and safe water. However, both human activities and natural events, including agriculture, sewage, industrial plants, and even Mother Nature, can lead to water pollution and poor water quality. To identify the impacts of this pollution and to implement appropriate measures to combat these impacts and prevent harm to human health and aquatic ecosystems, the continuous measurement and monitoring of water quality is essential. Traditionally, water quality is assessed by collecting samples at weekly or monthly intervals and analysing the physical, chemical, and biological characteristics of these samples in a laboratory. As rivers and large water bodies exhibit highly dynamic and often non-linear behaviour in both time and space, such low-frequency data collection makes it difficult to establish linkages between the cause and effect of pollution and to make timely decisions or develop potential remedies. Over the last few decades, however, advanced monitoring techniques that use multi-parametric autonomous sensor systems have been deployed to reduce the manpower requirement and facilitate real-time and remote water quality management. For instance, sensorized buoys and boats have been deployed for data collection and in-situ monitoring. To broaden the data coverage in space and time, multi-parametric sensor systems have also been deployed using aerial or underwater vehicles. Since the 1960s, three basic types of vehicles have been developed for water surveillance and monitoring, including human-occupied submersible vehicles, remote-controlled vehicles, and autonomous marine robots, or AUVs. Each type remains in use today and plays its own role in water research. Through recent years, autonomous underwater and surface vehicles have proven to be especially effective for maritime operations due to their large area monitoring capabilities and worry-free unmanned navigation. Autonomous underwater vehicles are programmable robotic vehicles that, depending on their design, can drift, drive, or glide through waters without real-time control by human operators. Until relatively recently, AUVs have been used for a limited number of tasks, dictated by the technology available. With the development of more advanced processing capabilities and high-yield power supplies, AUVs are now being used for more and more tasks, with roles and missions constantly evolving. Despite significant technological advances, however, AUVs often do not have access to global sensors to find their inertial state, or the states of the complex and changing environment in which they are operating. As a result, they require multiple local sensors on board to measure a range of different parameters that help to withstand environmental conditions. Various active sensing technologies, including sonar and vision or optical-based systems, have previously been employed for AUV depth and position sensing. However, these approaches generally suffer from significant disadvantages, including large size, poor resolution, and failure to function effectively in unsteady or turbid waters. Previous reports have also highlighted the severe consequences sonar can have on marine life. Considering this, there is a growing demand for low-powered, low-cost alternatives that can detect local pressure variations and help AUVs maintain desired depth and adequate positioning underwater, as well as to calibrate other sensors that may be on board when their response changes with pressure. For this, reliable, robust, flexible, lightweight, and surface-mountable sensing systems that can be readily deployed on AUVs are required. For reasons such as these, several flexible and conformable pressure sensors have recently been developed using a variety of electrical transduction mechanisms, including piezoresistive, piezoelectric, triboelectric, and capacitive pressure sensors. Among these, capacitive pressure sensors offer several advantages, including simple design, low-cost fabrication routes, fast response, long-term stability, and a lack of responsiveness to interfering stimuli, such as temperature. In addition, capacitive structures provide a passive form of sensing and thus low power consumption, thereby avoiding many of the issues associated with active sensors. Capacitive pressure sensors generally consist of two parallel, flexible, and conducting electrodes separated by a dielectric layer. In response to pressing or vibrating stimuli, the dielectric layer deforms, leading to an electric signal generation. Selection of the dielectric layer is therefore crucial to achieving a dynamic range and good sensitivity. Soft dielectric materials such as polyurethane and silicone-based elastomeric polymers such as PDMS have been widely used as capacitive pressure sensing dielectric layers. PDMS-based dielectric layers are attractive due to their excellent mechanical strength, tunable elasticity, flexibility, and conformability, as well as high dielectric constant. PDMS is also environmentally friendly and demonstrates high chemical stability and low sensitivity to temperature and humidity. On the other hand, this silicone-based polymer has an elastic modulus of 1 megapascal, which means PDMS-based capacitive sensors will experience small deformations under pressure and hence will have limited sensitivity range. Different material design strategies have been investigated to expand the detection range and improve sensitivity in PDMS-based capacitive sensors. For example, PDMS dielectric layers have been modified using high dielectric constant materials. Elastomers with micro or nanostructured features, including pyramids, pillars, and pores, have also been explored. This is because air gaps or pores formed in micro or nanostructured elastomers achieve high compressibility and thus enhance sensitivity. Highly porous, spongy elastomers have also shown stable pressure sensing over a wide detection range, up to 130 kilopascal. Dielectric layers such as these have previously been fabricated using sacrificial support materials. Due to its simplicity and versatility, this approach may therefore be used to develop tunable or large area flexible capacitive sensors that can be seamlessly integrated with a range of flexible electronic and robotic technologies. This work therefore presents a flexible and conformable porous elastomer-based capacitive pressure sensor that may be used for a wide range of pressure sensing applications. The porous elastomer-based capacitive pressure sensor was developed by simply sandwiching a porous elastomer between two gold electrodes on flexible Kapton substrates. First, the top and bottom contact electrodes were prepared by depositing an 80 nanometer thick layer of gold on the thermally resistive Kapton substrates using electron beam evaporation. The electrical connections were made by attaching wires to the flexible gold layer electrodes using a commercial conductive silver ink and epoxy for insulation. A dielectric layer with a thickness of 2 mm was then fabricated. This was done by casting a mixture of PDMS prepolymer and curing agent in a 10:1 weight per weight ratio with ammonium bicarbonate over the bottom contact electrode immediately after the mixture had been prepared. For this, PDMS and ammonium bicarbonate were mixed in a 4:1 weight per weight ratio. The counter contact electrode was then placed on top of the partially cured PDMS and ammonium bicarbonate film to ensure good adhesion. Finally, the capacitive structure was annealed to cure the PDMS prepolymer. At the same time, a dielectric layer with a high density of porous microfeatures was formed due to the decomposition of ammonium bicarbonate into ammonia, water, and carbon dioxide. The performance of the fabricated sensor was then characterized by applying pressures ranging from 0 to 300 kilopascal, similar to pressures experienced at approximately 30 meters below sea level. Figure 2a demonstrates the relative change in capacitance as a function of varying applied pressures in the range of 0 to 300 kilopascal. In this range, the porous elastomer-based soft pressure sensor demonstrated a near linear response with a 4% relative capacitance change from 2.9 to 3.5 picofarad. The sensor also presented a sensitivity of 0.7 per pascal. The capacitive sensor's response and sensitivity at stages of low, intermediate, and high pressures were also examined. In the low pressure regime, ranging from 0 to 25 kilopascal, the sensor demonstrated an increase in capacitance from 2.9 to 3 picofarad, resulting in an overall capacitance change of 4%. The sensor also showed a 97.2% linear response and a good sensitivity of 1.8 per pascal. In the intermediate and high pressure regimes, from 25 to 200 kilopascal and 200 to 300 kilopascal respectively, the sensor demonstrated capacitance changes from 3 to 3.3 picofarad and from 3.3 to 3.4 picofarad respectively, providing a relative capacitance change of 12 and 4.5% respectively. This resulted in a 99.2 and a 99.5% linear response, and sensitivities of 0.7 and 0.4 per Pascal respectively. The sensor also features fast response and good repeatability. Figure 2b presents the capacitive sensor's response in recovery time with loading and unloading of 20 kPa. When pressure was applied, the sensor's response time was 0.8 seconds, as can be seen in the top inset of Figure 2b. When the pressure was removed, the sensor's capacitance decreased with a recovery time of 1.2 seconds, as can be seen in the lower inset. The stability of the sensor was examined by cycles of loading and unloading of 20 kPa pressure. As shown in Figure 3a, the sensor demonstrated a stable change in capacitance without signs of fatigue, suggesting good durability. The slight drift in response can be handled with suitable readout electronics and requires further investigation. Figure 3b presents the sensor's capacitance changes when static pressures of 0 to 20 kPa were loaded and unloaded in a stepwise manner. The capacitance changed quickly and reversibly, indicating that the porous elastomer-based soft pressure sensor had stable response. In conclusion, a soft capacitive pressure sensor was fabricated by sandwiching a porous elastomeric dielectric layer between two electrodes on flexible Kapton substrates. The fabricated sensor was tested over a wide pressure sensing range under pressures similar to those experienced at up to approximately 30 meters below sea level. In this range, the sensor presented a 94.5% near linear response and sensitivity of 0.7 per Pascal. The sensor also featured fast response and recovery times as well as good stability, thus proving its applicability for a wide range of pressure sensing applications, particularly underwater robotics for real-time monitoring and surveillance operations. Our eventual aim is to deploy this flexible porous capacitive pressure sensor on marine robots for real-time water quality monitoring. Future work will therefore focus on exploring the performance of the fabricated sensor for depth sensing in both the laboratory and in real-world water environments. Before finishing, I would like to thank the BEST Group, the University of Glasgow, the James Watt Nanofabrication Centre, EPSRC, and the European Commission for making this work possible. And thank you to everyone who has listened. If you do have any questions, please feel free to reach out to us.